Hello everyone. In this video I will be covering the nucleophilic substitution of a secondary halogenoalkane, which is a good example because it undergoes both SN1 and SN2 mechanisms to differing degrees, as well as it's a good example to demonstrate the inversion of chirality, which I spoke of when I covered the SN2 mechanisms in previous videos. The secondary halogenoalkane chosen in this example is 2-chlorobutane, in which, if you notice, the carbon bonded to the halogen group has been denoted with an asterisk to indicate that it is a chiral carbon. A chiral carbon is a carbon atom bonded to 4 different groups. In this example, this chiral atom is bonded to the methyl group, the hydrogen atom, the chlorine atom, and the ethyl group, and thus it is considered as a chiral carbon. It's a good point here to leave this example for a minute or two to discuss briefly what stereoisomers, enantiomers, which are a type of stereoisomer called optical isomers, are. I have used the product formed from the reaction of 2-chlorobutane with the hydroxide nucleophile. The major reaction that occurs is that the hydroxide ion substitutes the chlorine atom to form butan-2-ol plus the chloride ion. As you can see here in the product, butan-2-ol, the carbon atom denoted with an asterisk, is still a chiral carbon since it's still bonded to 4 different groups: the methyl group, the hydrogen atom, the hydroxyl group, and the ethyl group. So I'm going to use this compound to briefly discuss chirality, which I've drawn here. The chiral carbon is drawn using a stereochemical formula to show the spatial 3D arrangement of atoms bonded to it, of groups bonded to it, sorry. This, as you can see here, this chiral carbon is bonded to a hydroxyl group, the ethyl group, the methyl group, and the hydrogen group. When a compound, when a chiral carbon exists within a compound, this compound has optical isomers called enantiomers, which are non-superimposable mirror images of one another. As you can see here, I've drawn the stereochemical formula of its mirror image, in which the hydroxyl groups are in the same positions. The ethyl groups point outwards in each, and the hydrogen and methyl groups are mirror images of one another. If I were to rotate this compound in this direction to explain what non-superimposable means, if you can see here, this is enantiomer A, which has been drawn here, and I simply rotated this clockwise to place the C2H5 ethyl group in the same position as this compound. If I were to superimpose these two molecules or enantiomers onto each other, the OH, the hydroxyl group, the hydroxyl groups, as well as the ethyl groups, would superimpose, meaning they would be overlapping in the same position. But the two other groups would be in different positions. The methyl group here would superimpose with the hydrogen atom, and the hydrogen atom here would superimpose on a methyl group. Thus, these compounds, which are called enantiomers, which are mirror images of one another, are non-superimposable. If I were to align the hydrogen and the methyl groups together, still the ethyl and the hydroxyl groups won't align. And thus, these are called enantiomers, which have some different properties and some of the same properties, which we will discuss in later videos. I just wanted to briefly discuss them because they are relevant to this example. Therefore, let's get back to our example. As I stated previously, the 2-chlorobutane undergoes a nucleophilic substitution in which the hydroxide ion substitutes the chlorine atom to form butan-2-ol via a nucleophilic substitution reaction. Since this is a secondary halogenoalkane, it will undergo both SN1 and SN2, which I will explain below here. I would start by drawing an SN2 mechanism. Just a quick recap, the SN2 mechanism is a one-step mechanism which involves the formation of a transition state that has a high activation energy and is a stereospecific reaction, meaning this reaction will only produce one enantiomer of this molecule. As you can see here, this is my chiral carbon. This is my chiral carbon right here, denoted with an asterisk. We've drawn SN2 using stereochemical formulas, and it's clear here that the attacking group, the nucleophile, always attacks from the opposite side of the leaving group by donating a pair of electrons to the partially positive carbon bonded to the partially negative, more electronegative chlorine atom. What happens is as the OH is forming a bond, the Cl group leaves via the chlorine atom leaves via heterolytic fission, gaining both these electrons, one of which belongs to the chiral carbon atom. This process goes through a transition state, as stated previously in other videos, in which the hydroxyl group is now partially bonded to the chiral carbon, as well as the leaving group is partially bonded. Thus, as the hydroxyl is forming a bond with the chiral carbon, the chlorine atom is leaving, and these dashed lines represent partial bonds. The charge of the transition state is negative, same as the charge of the nucleophile. The reaction then proceeds by the chlorine atom leaving. And as you can see here, I've drawn the inversion of configuration, or chirality, in which, since as stated previously, since the attack of the hydroxide ion is one-sided only, it will always attack from the opposite side of the leaving group, inverting these bonds pointing to the left, pointing to the right, inverting them to the left, it only forms one enantiomer. If the hydroxide ion were able to attack from this is called the front side, this is the back side of the molecule, the side of the halogen is to the front side, in which the hydroxide ion cannot approach this chiral carbon due to steric hindrance from the side of the chlorine atom, as stated previously. Thus, the OH, the hydroxide ion, attacks from the opposite side of the halogen, the leaving group, and thus the inversion is always one-sided. These bonds will always invert to one side, which is the opposite side of which the nucleophile attacks, as shown in this molecule here. Thus, it will only form one enantiomer of this molecule, since the attack of the hydroxide ion is one-sided only, and thus inversion is one-sided. This is what is meant by a stereospecific reaction. It means that only one enantiomer will always form from this mechanism. On the other hand, if we consider the SN1 mechanism for the same reaction, quick recap, it's a two-step mechanism which involves the formation of a carbocation intermediate, and this is a non-stereospecific reaction, which I will discuss in a bit. It's a two-step mechanism. Step one is the slow rate determining step. As stated in previous videos, this carbon atom, this chiral carbon atom bonded to the leaving group, has high steric hindrance, and thus the hydroxide nucleophile ion cannot attack this carbon directly. What happens is it goes through an intermediate, that is carbocation intermediate, which is formed by the heterolytic fission of this chlorine atom, which gains both these electrons to form a trigonal planar geometry for this secondary carbocation. The second step involves the attack, which is the fast step. This is the rate determining step because this has high activation energy, which high activation energy is required to form the somewhat unstable carbocation intermediate, followed in step two by the fast step, which forms a stable molecule that has lower activation energy, and thus this is the fast step. The hydroxide nucleophile donates a pair of electrons to the carbon atom with a formally positive charge, forming butane 2O. In this mechanism, on the other hand, this carbocation intermediate has a trigonal planar geometry as displayed here. This carbocation intermediate has a 50-50% chance of attacking the carbocation from the top part of the plane or from the bottom part of the plane. If the attack was from the bottom, the bonds made with the methyl, ethyl, and hydrogen atoms would invert upwards. On the other hand, if the attack was from the top part of the trigonal planar carbocation, these bonds would invert downwards, producing both mirror image enantiomers. If you were to rotate this molecule, you would form both enantiomers equally. 50% chance of forming enantiomer A and 50% chance of forming enantiomer B. And this is what is meant by a non-stereospecific reaction. It's not specific to the formation of one enantiomer only. It forms both enantiomers equally. There's an equal chance of forming each enantiomer, and thus this is a non-stereospecific reaction. It's not specific to one enantiomer. On the other hand, the SN2 mechanism is a stereospecific reaction because inversion is only one-sided, and thus it would form just one of the enantiomers. One question that the IB has asked, I think it was the year paper 2, November 2017 time zone, is explain. I'm not sure if this was the same molecule they chose, but it was a secondary halogenoalkane. This question stated to explain why the reaction of 2-chlorobutane with NaOH, which is a nucleophilic substitution reaction, and this is a secondary halogenoalkane, just as the example we covered in this video, produces 75% of one enantiomer and 25% of the other. The answer is as follows. 2-chlorobutane is a secondary halogenoalkane, and thus 50% of these molecules would undergo SN1, and the other 50% would undergo SN2 mechanisms. The SN1 mechanism is a non-stereospecific mechanism, and thus would form each enantiomer in equal amounts, and thus I've divided the 50% to form 25% of enantiomer A and 25% of enantiomer B. On the other hand, the other 50% undergo a stereospecific mechanism which forms one of the enantiomers, and thus all the 50% of these molecules form a single enantiomer, which I chose as enantiomer B in this example. Thus, this reaction overall would produce 75% of enantiomer B and 25% of enantiomer A. I would also like to add a note regarding why secondary halogenoalkanes undergo both SN1 and SN2 mechanisms at the same time. Remember from previous videos the major points that need to be discussed regarding why a certain nucleophilic substitution reaction undergoes either SN1 or SN2 are the steric hindrance surrounding the carbon atom bonded to the halogen group, as well as the stability of the carbocation intermediate that forms here. And for both these points, this secondary halogenoalkane has intermediate steric hindrance when compared to primary or tertiary halogenoalkanes, in the sense that it's bonded to 3 alkyl groups and 1 small hydrogen atom, and thus there's some small space here on the back side of the molecule for the OH to approach and form the transition state and undergo an SN2 mechanism. On the other hand, if it were to undergo an SN1 mechanism, in which the heterolytic fission of the chlorine atom forms a secondary carbocation intermediate. In this case, the carbocation intermediate is intermediate in stability since it's stabilized by 2 positive inductive effects. Thus, in terms of steric hindrance, as well as the stability of the carbocation intermediate, a secondary halogenoalkane is somewhat intermediate in both between a primary and a tertiary halogenoalkane, and thus it undergoes SN1 or SN2. please keep in mind that depending on the choice of the nucleophile, as well as the choice of the solvent for a secondary halogenoalkane, one mechanism can be favored more over the other, and thus it wouldn't form a 50-50 percent. It wouldn't form a 75-25% as the example we discussed previously. Thus, this can be altered by depending on the strength of the nucleophile in terms of its nucleophilicity, as well as the choice of solvent, which could favor either SN1 or SN2. Thus, if one were to choose an aprotic solvent for a secondary halogenoalkane, the aprotic solvent favors the SN2 mechanism to occur. On the other hand, if you were to choose a protic solvent, a polar protic solvent, that would favor the SN1 mechanism to take place with a higher percentage. Thank you for watching again.